All right, let's look at some exercises from section 10.3. Now, 10.3.10 talks about computing the Euler phi function. And just to remind you, phi of n is equal to the number of positive integers less than n and relatively prime to n. Okay, so less than n and relatively prime to n. So for instance, you have phi of 1. Phi of 1 is 1. Phi of 2 is 1 also, because 1 is the only number less than 2 that's relatively prime to 2. Phi of 3 is 2. Phi of 4, well, let's see. 1 and 3 are relatively prime to 4, so phi of 4 is 2, and so on. All right, now let's consider phi of p squared, where p is prime. Now, it's good to do examples to see how this works, and then see if you can generalize. So let's consider p equals 5. All right, then phi of p squared is phi of 25. So here I write the integers from 1 to 24. I know that I can only go up to 24 because phi only counts the positive integers less than n, so I'm looking at the numbers less than 25. All right, so there are 24 numbers less than 25, but some of them are not relatively prime to 25. Which ones are not relatively prime? Well, there's 5, 10, 15, and 20. All right? So how are we counting these up? 24 is 25 minus 1. And 4, which is the number of numbers that are not relatively prime, I have 4 numbers that are not relatively prime. The 4 is 5 minus 1. Why? Because I have the first multiple of 5, second multiple, third multiple, fourth multiple. The fifth multiple of 5 is 25, so I'm not counting that. So here I have 24 numbers, and I subtract 4, so it's 25 minus 1 minus 5 minus 1, and the result is 20. So see if you can generalize to an arbitrary prime. Okay, you can use the same reasoning. All right. Now another similar problem is phi of pq, where p and q are primes and p is unequal to q. You can do a similar kind of counting argument. Consider phi of 15. So I wrote the numbers from 1 to 14 in a line, and then I have to cross out the ones that are not relatively prime to 15. So what are they? First of all, they're the multiples of 3. 3, 6, 9, 12. 4 of them. Then they're multiples of 5, because 5 and 15 are not relatively prime. So there's 5 and 10. There's 2 of them. Now notice that the 4 multiples of 3, 4 is 5 minus 1, and 2 is 3 minus 1. So the total number of numbers relatively prime to 15 and less than 15 are 15 minus 1 minus 5 minus 1. I'm subtracting multiples of 3, and I'm subtracting multiples of 5. Okay, and then you get this answer. So see if you can generalize to arbitrary p and q. Okay. All right, now let me do one more exercise from 10.3. Let G be a group of prime order. Now in the 10.3.17 it says use Lagrange's theorem. I think it's better to use proposition 10.3.16. Use proposition 10.3.16 to show that the only proper subgroup of G is the trivial subgroup E. Now proper means strictly smaller than, or strictly contained in. Right? It can't be G itself. It has to be something smaller than G. All right. So proposition 10.3.16 says let the order of G be P where P is prime, then G is cyclic, and any element of big G which is not the identity is a generator. All right. So what we're trying to show is that the only proper subgroup of G is the trivial subgroup. So we can do that by showing that any subgroup of G that is not the trivial subgroup must be all of G. And that's what we're going to do. So let H be a subgroup of G where H is not the identity. If H is not the identity, then there must exist some element other than the identity which is in the subgroup. So there must exist a G, which is in big H, where G is not the identity. And then by proposition 10.3.16, what do you conclude about the set generated by G? Now, and then you have by the closure property, the set generated by G is contained in something. So by substitution, it follows that something. So you can follow this outline to prove this. Okay. So it means so I can say so the only subgroups. So the only subgroups of G are the identity and ... So you can fill in those blanks, and that will give you the proof that you need. Okay.